Okay, section 2.5, continuity. Okay, let's look at the following graphs. Can I get them all on there? Just about. Okay, in the above graph, this one right here, the curve continues without interruption through the point AL. We say the curve is continuous at A. There are no gaps, breaks, or holes in the graph at x equal A. Notice f of A would equal L, or f of A is defined. The limit as x goes to A of f of x would be L, or the limit exists. And 3, that limit and the functional value are equal to each other. Okay, next picture, we got a new function. We're missing a single point at A. Recall an open circle in the graph represents a missing point. The above graph has a hole where the point AL would be. We say the above curve is not continuous at x equal A, or is discontinuous at A. Note also that f of A is undefined. The discontinuity shown here is a removable discontinuity. Removable because we can matter affixing just a single point, and we could remove that discontinuity. But there's a hole in the graph, so we have a discontinuity. Next picture here. In the above graph, the graph breaks into two pieces at x equal A. We say the curve is not continuous at x equal A, or is discontinuous at x equal A. Note the limit as x goes to A of f of x does not exist. This discontinuity here is called a jump discontinuity, because it looks like in this case, if you're walking along the curve from left to right, you would have to jump down. Maybe it's another curve you'd have to jump up, but that's a jump discontinuity. Next graph. In the above graph, there's a hole in the main curve, and there's a point directly below the hole. We say the curve is not continuous at x equal A, or is discontinuous at x equal A. Note here the limit as x goes to A of f of x does not equal f of A, or L does not equal M. The discontinuity shown here is, again, a removable discontinuity. Removable, again, because if we could just move that one point so that everything was lined up, you'd fix it. In the graph above, the last graph here, in the graph above, the curve breaks into two pieces at x equal A. We say the curve is not continuous at x equal A, or is discontinuous at x equal A. Note also that both f of A is undefined, and the limit as x goes to A of f of x does not exist. The discontinuity here is called an infinite discontinuity. So this guy up here, where the graph just continued on with no gaps, breaks, or holes, this was continuous at A. Each and every other of these ones where we had a hole, or this big break, or another hole, or breaking up and going off to infinity, those are all discontinuous at A. You have discontinuities at any place the graph has a gap, break, or hole. And so that's kind of what we have here. Graphically, a curve is continuous if there are no gaps, breaks, or holes. In a continuous function, the graph is presented in one piece. A curve is not continuous or is discontinuous at any x value where there's a gap, break, or hole. And then here's our official definition. A function is continuous at x equal A if the following conditions are satisfied. 1, f of A is defined. 2, the limit as x goes to A of f of x exists. 3, the limit as x goes to A of f of x equals f of A. Note the above three conditions is equivalent to saying that a function is continuous at x equal A if the limit as x goes to A of f of x equals f of A. And you will see that in more advanced textbooks. We will be using the three conditions there. So, right here, you will be asked on a quiz or test to state the three conditions necessary for a function f of x to be continuous at a number A. To receive credit, you must respond with. You write those three things down. If you don't write those three things down, no credit. And that's what it says here. Credit will be awarded for only perfectly stated answers. No partial credit will be awarded for imperfect answers. So you memorize this. Okay, let's work on some problems. We're going to do graphing things first. Say where the following fails to be continuous at y. At each discontinuity, we give both the condition of continuity that fails and what type of discontinuity there is. So we're going to work our way left to right. And so we'll kind of do a little chart here. What the discontinuity is. condition that fails, and the type. And let's remember my conditions are 1, f of a is defined. 2, the limit as x goes to a of f of x exists. 3, the limit as x goes to a of f of x equals f of a. So working my way left to right, my first discontinuity would be right about there at that hole. That looks like it's x equal negative 3. And the condition that fails here is that f of negative 3 is undefined. We have a limit. The limit, if I trace both sides with my fingers coming closer and closer and closer, it looks like the limit would be 3. But there is no functional value because you have that open circle, which means there's not a y-coordinate, and so I don't have my function being defined. And my type, that's not how you spell type, and it's almost illegible. The type of discontinuity I have, that would be a removable discontinuity, because I can just fix one point. So on to the next one, left to right, that would be x equals 0. And the condition that fails here is that the limit does not equal the functional value. The limit, coming closer and closer and closer, the limit, my y-coordinate right between my thumbs there, well, the limit would be 0, but the functional value down at that actual open closed circle would be negative 2. And so my limit does not meet my functional value. So there's the condition that fails, and that too is removable discontinuity. On to the next one. It looks like that's about x equal 1.5. And anytime we're doing things graphically, it's ballpark. Now, generally I say don't give me decimals unless I give you decimals. But when we're doing things graphically, kind of all bets are off. It's always ballpark. But at 1.5, and here we've got a couple conditions that are failing. In fact, actually all 3 of them fail. F of 1.5 is undefined. The limit as x goes to 1.5 does not exist. And so then automatically condition number 3 too. And truthfully, condition 3 is always going to fail. If either condition 1 or condition 2 fail, then condition 3 has to fail automatically. I'm just writing down each thing that's going wrong. On a test or quiz, you could just give me the first one that comes along, but give me the first one. Don't always just write down number 3. Give me the first one. And this guy would be called an infinite discontinuity. Going off to the next one, we've got x equal 1, 2, 3, it looks like. And what we've got going on here is that there's not a limit. Limit as x goes to 3 of f of x does not exist. We do have a functional value because there's an open circle, or closed circle, excuse me, but no limit. As I trace both sides of my fingers together, they aren't going to come close to meeting, so no limit. And this is called a jump discontinuity. And we'll do the last one up here. Last discontinuity would be at x equals, and it looks like x equal 8. I'll bring it down so you can see it. Maybe if I go out a little bit. Yeah, there we can see everything. X equal 8. And again, what's going on here, you got two things. F of 8 is undefined, and the limit doesn't exist. And obviously the third one always fails, but the first two there fail, and this is called a jump discontinuity as well. But what we're looking for in each case are the gaps, breaks, and holes. And we'll end this video.